When dealing with multiple conduits containing service conductors, the question of grounding arises, specifically whether a separate ground wire is needed for each conduit. According to the National Electrical Code, specifically Section 310.15b6, where insulated or covered conductors of different systems are installed in a raceway, they must be grouped together and enclosed by a metallic sheath, grounded metal raceway, or other suitable means. This section addresses situations where conductors from different electrical systems occupy the same raceway. However, in the scenario presented, the conductors are from the same system but are split into two conduits. The key principle here is ensuring that a low impedance ground fault path exists to facilitate the operation of overcurrent protection devices such as circuit breakers or fuses. This path allows sufficient fault current to flow back to the source, causing the protective device to trip and energize the circuit, thereby minimizing the risk of electrical shock or fire. In the described setup, there are two conduits. One conduit contains three 350 kcm aluminum conductors for the service, and the other conduit contains three 350 kcm aluminum conductors along with one 4/0 aluminum ground wire. 4/0 aluminum ground wire in one conduit serves as the equipment grounding conductor for both sets of 350 kcm conductors. This arrangement is permissible because the code allows for a single equipment grounding conductor to serve multiple circuits or conductors within the same system, provided that the grounding conductor is adequately sized to handle the potential fault current from all the conductors it serves. The size of the equipment grounding conductor is determined by NEC Table 250.122, which relates the size of the ungrounded conductors to the minimum size of the equipment grounding conductor. For 350 kcm aluminum conductors, a 4/0 aluminum ground wire is typically sufficient, but it is crucial to verify this based on the specific installation and the applicable codes and standards. The grounded metal raceway, or in this case, the conduit itself, if it is metal and properly grounded, also contributes to the ground fault path. However, relying solely on the conduit for grounding is generally not recommended as the primary means of grounding due to the potential for loose connections or corrosion, which can increase impedance and reduce the effectiveness of the ground fault path. Therefore, the presence of a dedicated equipment grounding conductor is essential. The NEC mandates that the equipment grounding conductor be installed in close proximity to the circuit conductors to minimize impedance. This is why the 4/0 aluminum ground wire is run within one of the conduits along with the 350 kcm conductors. This arrangement ensures that the ground fault path has the lowest possible impedance, which is critical for the reliable operation of overcurrent protection devices. It is also important to note that all connections within the grounding system must be made with listed and labeled connectors suitable for the purpose. These connectors are designed to provide a secure and reliable electrical connection that will not loosen or corrode over time. Furthermore, the grounding system must be properly bonded to all metal enclosures and equipment to ensure that there are no voltage differences between them. This bonding helps to prevent electrical shock hazards and ensures that the entire electrical system is at the same ground potential. In summary, based on the information provided in the relevant NEC guidelines, one 4/0 aluminum ground wire in one conduit is sufficient for grounding both sets of 350 kcm aluminum conductors. However, it is essential to verify that the 4/0 aluminum ground wire is adequately sized for the potential fault current and that all connections are made with listed and labeled connectors. Additionally, the grounding system must be properly bonded to all metal enclosures and equipment to ensure safe and reliable electrical installation. When working with electrical systems, it is always advisable to consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and standards. Electrical codes and standards are constantly evolving, and it is crucial to stay up to date with the latest requirements to ensure the safety and reliability of electrical installations. The 4/0 aluminum ground wire provides a dedicated low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protection devices. The NEC emphasizes the importance of minimizing impedance in the ground fault path. The closer the equipment grounding conductor is to the circuit conductors, the lower the impedance will be. This is why it is recommended to run the ground wire within the same conduit as the phase conductors. It is also essential to ensure that the conduit itself is properly grounded. If the conduit is metal, it can serve as an additional ground fault path. However, it should not be relied upon as the sole means of grounding. The equipment grounding conductor should always be present to provide a dedicated ground fault path. When sizing the equipment grounding conductor, NEC Table 250.122 provides guidance. This table relates the size of the ungrounded conductors to the minimum size of the equipment grounding conductor. For 350 kc mil aluminum conductors, a 4/0 aluminum ground wire is typically sufficient. However, it is important to consult the table to ensure that the ground wire is adequately sized for the specific installation. All connections in the grounding system must be made with listed and labeled connectors. These connectors are designed to provide a reliable electrical connection that will not loosen or corrode over time. The use of proper connectors is essential for maintaining the integrity of the grounding system. In addition to the equipment grounding conductor, all metal enclosures and equipment must be properly bonded to the grounding system. Bonding ensures that all metal parts are at the same ground potential, which helps to prevent electrical shock hazards. The NEC provides specific requirements for bonding in Article 250. When working with electrical systems, it is always important to follow safe work practices. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and energizing circuits before working on them. It is also important to have a thorough understanding of the NEC and other applicable codes and standards. The NEC is a complex document, and it can be difficult to interpret without proper training and experience. Therefore, it is always advisable to consult with a qualified electrical engineer or inspector when working on electrical systems. Grounding is a critical aspect of electrical safety. A properly installed and maintained grounding system helps to protect people and equipment from electrical shock and fire hazards. By following the NEC guidelines and best practices, it is possible to ensure that electrical systems are safe and reliable. The installation should be inspected and approved to ensure compliance with all applicable codes and standards. The inspector will verify that the equipment grounding conductor is properly sized, that all connections are made with listed and labeled connectors, and that all metal enclosures and equipment are properly bonded. The inspector may also perform tests to verify the integrity of the grounding system. These tests may include ground impedance measurements and continuity tests. Ground impedance measurements are used to verify that the ground fault path has a low impedance. Continuity tests are used to verify that all metal parts are properly bonded to the grounding system. If the inspection reveals any deficiencies, they must be corrected before the electrical system is put into service. It is important to address all deficiencies promptly to ensure the safety and reliability of the electrical system. Regular maintenance is also essential for maintaining the integrity of the grounding system. This includes inspecting connections for tightness and corrosion and testing the grounding system periodically. Any loose or corroded connection should be tightened or replaced. The grounding system should also be tested periodically to verify that it is still functioning properly. If the tests reveal any problems, they should be addressed promptly. By following a regular maintenance schedule, it is possible to ensure that the grounding system remains effective and that the electrical system is safe and reliable. The equipment grounding conductor, often referred to as the EGC, is a critical component of the overall grounding system. Its primary function is to provide a low impedance path for fault current to return to the source in the event of a ground fault. This low impedance path is essential for ensuring that overcurrent protection devices, such as circuit breakers or fuses, operate quickly and effectively to clear the fault and prevent electrical shock or fire hazards. The size of the equipment grounding conductor is determined by the size of the ungrounded conductors in the circuit. NEC Table 250.122 provides specific guidelines for sizing the EGC based on the ampacity of the ungrounded conductors. It is important to consult this table carefully to ensure that the EGC is adequately sized for the potential fault current. The material of the equipment grounding conductor can be either copper or aluminum. Copper is a better conductor of electricity than aluminum, but aluminum is less expensive and lighter in weight. Both copper and aluminum EGC are permitted by the NEC, but it is important to select the appropriate size and type of conductor for the specific application. The equipment grounding conductor must be installed in close proximity to the circuit conductors. This is typically achieved by running the EGC inside the same raceway or cable assembly as the phase conductors. Installing the EGC close to the phase conductors minimizes the impedance of the ground fault path and ensures that fault current can flow back to the source quickly and efficiently. The equipment grounding conductor must be connected to all metal enclosures and equipment in the electrical system. This bonding ensures that all metal parts are at the same ground potential, which helps to prevent electrical shock hazards. Bonding is typically achieved by using bonding jumpers or bonding screws to connect the EGC to the metal enclosures and equipment. The NEC provides specific requirements for bonding in Article 250. The grounding electrode system is another critical component of the overall grounding system. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provides a path for fault current to dissipate into the earth. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The NEC provides specific requirements for grounding electrodes in Article 250. The grounding electrode conductor, or GEC, connects the grounding electrode system to the electrical system. The GEC must be sized according to NEC Table 250.66. The GEC must be connected to the neutral point of the electrical system, typically at the service entrance. The GEC must also be connected to the equipment grounding conductor system. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line transients. SPD are typically installed at the service entrance and at individual equipment locations. SPD work by diverting surge current to ground, thereby protecting the electrical equipment from damage. The NEC provides specific requirements for SPD in Article 285. It is important to select SPD that are appropriate for the specific application and to install them according to the manufacturer's instructions. Regular inspection and testing of the grounding system are essential for ensuring its continued effectiveness. The grounding system should be inspected periodically for any signs of damage or corrosion. The grounding connections should be checked for tightness and the grounding electrodes should be tested for their resistance to ground. Any problems that are identified during the inspection should be corrected promptly. A properly installed and maintained grounding system is essential for electrical safety. By following the NEC guidelines and best practices, it is possible to ensure that electrical systems are safe and reliable. The 4/0 aluminum wire serves as the equipment grounding conductor, also known as the EGC. The purpose of the EGC is to provide a low impedance path for fault current to return to the source, which facilitates the quick tripping of overcurrent protection devices like circuit breakers or fuses. This rapid clearing of the fault minimizes the risk of electrical shock and fire. The National Electrical Code, or NEC, dictates the requirements for grounding and bonding electrical systems. Adherence to these requirements is crucial for ensuring safety and compliance. The size of the EGC is determined by the size of the ungrounded conductors, as specified in NEC Table 250.122. For 350 kc mil aluminum conductors, a 4/0 aluminum EGC is typically sufficient, but it is always necessary to verify this based on the specific installation and applicable codes. All connections within the grounding system must be made with listed and labeled connectors. These connectors are designed to maintain a secure and reliable electrical connection over time, preventing loosening or corrosion. It is also vital to properly bond all metal enclosures and equipment to the grounding system. Bonding ensures that all metal parts are at the same ground potential, reducing the risk of electrical shock. Article 250 of the NEC provides detailed requirements for bonding. Grounding is a fundamental aspect of electrical safety, and a properly installed and maintained grounding system is essential for protecting people and property from electrical hazards. When working with electrical systems, it is always best to consult with a qualified electrical professional to ensure compliance with all applicable codes and standards. This is to make certain that the installation is safe and reliable. The NEC is regularly updated, so it's important to stay informed about the latest requirements. Code updates can impact grounding and bonding practices, so it's crucial to keep up with the changes. The 4/0 aluminum ground wire being installed in one of the conduits provides an adequate grounding path for both conduits. The NEC allows for a common grounding conductor for multiple circuits or conductors within the same system as long as the conductor is properly sized. In this case, the 4/0 aluminum wire meets the size requirements for the 350 kc male conductors. Therefore, there is no need to install a separate 4/0 ground wire in each conduit. This arrangement is both compliant with the NEC and cost-effective. However, it is essential to ensure that the connections to the ground wire are properly made and that the entire grounding system is properly bonded. The integrity of the grounding system is crucial for electrical safety. A properly grounded system helps to prevent electrical shock and fire hazards. By following the NEC guidelines and best practices, it is possible to ensure that electrical systems are safe and reliable. The NEC is a comprehensive set of rules and regulations that govern the installation and maintenance of electrical systems. It is important to have a thorough understanding of the NEC in order to ensure that electrical work is performed safely and in compliance with applicable codes. The NEC is updated every 3 years, so it is important to stay up to date with the latest changes. There are many resources available to help electrical professionals stay informed about the NEC. These resources include training courses, seminars, and online publications. By taking advantage of these resources, it is possible to stay abreast of the latest developments in the electrical industry and to ensure that electrical work is performed safely and in compliance with applicable codes. When working with electrical systems, it is always important to exercise caution and to follow safe work practices. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and energizing circuits before working on them. It is also important to have a thorough understanding of the electrical system before beginning any work. By following these precautions, it is possible to minimize the risk of electrical shock and other hazards. Electrical work should only be performed by qualified and licensed professionals. This is to ensure that the work is performed safely and in compliance with applicable codes.